Good afternoon, everyone. I hope the previous sessions have indeed given you a grip over AI. We have almost reached the midpoint of the STTP program. To take it further, we are planning to match the AI with blockchain in the coming sessions. It gives me a great pleasure to welcome you all to this session, Blockchain and AI, a perfect match. The session will be handled by Dr. Krishna Pratap Singh, Associate Professor, Department of Information Technology, Indian Institute of Information Technology, Allahabad. His research interests mainly include machine learning, optimization, and evolutionary algorithms. He has published extensively in journals and has presented in many conferences of international repute. Apart from teaching, he is also involved in many prestigious projects. We are indeed lucky to have him today with us. Hope you all benefit from his insights on blockchain and AI. Over to you, sir.
Thank you, Professor Thomas, for kind introduction. Let first I will share my PPT, then I will start. Is it visible? My PPT slides are visible?
Yes, sir, your PPT is visible.
Okay, thank you. Thank you again for a kind introduction, and thank you to all to joining this session. So good afternoon to all of you. What already Professor Thomas said that in the previous sessions have been covered about AI and other approaches. What you are going to get in this lecture is basically the AI, especially how this privacy preserving things are important for the machine learning part, and how we can handle the security issue in the machine learning, or in other way around, for a particular application of a machine learning algorithm in different domain, what we need to preserve the privacy of the individual also. If we are able to do so, then the advantage is then we may get more closure application. Closure means what I am saying, more real life applications, including in the health, finance, everywhere, where as an individual or as a country, everyone wants to control the data sets. Data sets are not freely available. It's not like that anyone can go and take your own data. But at the same time, the backbone of machine learning and deep learning models are they require data sets. So there is a contradiction. We all are saying that we need a good machine learning and deep learning AI algorithm to solve the problem. But the need for these techniques are basically, can we have a fair amount of data sets so that better learning, better interpretation, we can do that. But at the same time, for the data set point of view, if you all are aware about that, each country, even the government of India, is saying that the bigger company must install their data server at different location in India only. Why this? There are any data, privacy of the data is so important. But at the same time, each individual on the mobile phone also are capturing so many data sets. But at the same time, we don't want to share every data sets to every individual or any common person or any industry, though knowingly or unknowingly right now we are giving, but we want to preserve our data sets. But at the same time, as a user, as a country, we want to participate in the learning algorithms so that we can serve the humanity in the better way. So how this contradiction we can solve? So in this whole talk, what you can expect are going to get the two component. 50% of the talk, I will talk about AI and machine learning basically, and transfer learning and meta learning part. And then I will try to connect this, the need of the privacy of these approaches, why we need the privacy to preserve these algorithmic part. And this, so in the later half, I will introduce differential privacy in the machine learning, not in the data. And then I will talk about federal learning. can we perform this federal learning is very much useful even in the edge computing. So this way the whole talk will be how to machine learning and the need and how we can handle up to certain extent in the current state of the art where worldwide people are working to make this learning to be a federal or more participatory, but at the same time preserving the data. So to begin with, the first half, what I said, I'm going to talk about the machine learning, brief introduction about that, transfer learning and meta learning for that. And then I will come up on this. So to begin with, 1 minute. Okay. What is machine learning? Let's start with this. I came to know, but other speakers have covered. So quickly, I will move ahead. How individual as a human we are learning. If you have any observation in your home, how the kids are learning, if you have seen that, the 2 years or 3 years old kid, how he or she is learning. The God gifted, you can say, the brain and everything is there for the kid, but you don't know the face. This face is for human, this face is for cat, this face is for dog. But after a certain time of the intervention of the knowledge sharing by the parents, somehow he or she is able to recognize that this one is a cat, this one is a dog. So the first part, what a kid is doing, the vision part, and then the brain develop after certain 6 7 years. After that, he or she is able to more, you can say, about the language term, language understanding develop. So first vision comes out and then language comes out. So kids have, you can say, the way of adopting from the parents, from the nature, and he or she is able to learn. Same way, how this machine learning is nothing else but algorithm which we talk about, how it can learn. So this picture, intentionally, I have put it here, one robot and one kid, both are trying to learn. The same way we have to nurture how we are training the kid, the same way the machine learning algorithms are required to train. So by the mathematical definition, what we can say, a computer program set to learn from the experience E with respect to some class of task T and performance measure P if its performance at the task T is measured by P improves with experience. What it means in the classroom teaching, what we are doing, that we took some exam, some performance, and then we see that how students are performing in the particular text. So that's the measure, performance measure we do to learn the specific learning outcome of a student. He is or she is able to learn or not. Same way we do this process for a machine learning for a particular task. It may be a clustering, it may be a classification of cat or dog. Is it learning is happening, means if performance is improving or not. That's what the machine learning is. I will not go into detail of each and every algorithm, but what happened, always we come up with the issue in the machine learning is bias and variance or overfit or underfitting. Again, I will connect to the classroom teaching here. What happened in the classroom teaching? One student is solving, there are 100 problems. He or she is just solving all the problems, just doing too much. So it means somehow he or she is he is able to memorize every steps. Then what happened? If any new problem comes out, problem new, if I am saying, means not covered in the set which he or she has solved, then what happened? Any new problem comes out, since he has done a lot of practice for the set of particular questions, so he or she has memorized the concept. So any new different kind of problem comes out, he or she may not able to solve. I'm saying may not, maybe someone can solve also. So such kind of condition is also happened in the machine learning. If your training is too much, that during the training performance is too good, means 100% each thing you are able to solve, but the testing is coming, new data sets are coming. In that case, if algorithms is not going to perform well, suppose 100% accuracy during the training and only 10% during the testing, in that case, it becomes overfitting case. or spoon feeding. That's what we do. We say in the home or in the classroom, don't do too much spoon feeding. Let students learn by doing, by understanding, by their own also. Every step as a teacher, if I say do left, right, this, that, then his her mind will not work. Same way will happen with the machine learning algorithms. Also, because we want to be model as adaptive model to work in the new problem. So the overfitting is a phenomena. Cutting down because we had time restrictions and also the putting in the federal part. Overfitting is a phenomena. What you can say, if the training and testing what we do in the machine learning algorithms. So overfitting means if the training performance is good, testing is poor, then it's overfitting. The reverse, if the training is poor, then the of course testing will be fluctuation, it will be underfit, no training at all. So there are two kind of phenomena, and in the machine learning algorithms, every time we try to make a balance between this underfit and overfits, and that's how this machine learning algorithms is slightly differ compared to the statistical method. Otherwise, many things have been borrowed, but this concept of generalization makes this the difference between machine learning and pure statistical techniques. That's what the underfit and overfit in this. And what are the three important parts in the machine learning is, or any deep learning part, three important. We need a representation. Representations means how to represent, like to understand, for the sake of simplicity, to understand the language, what you need a representation. And one representation may be English language A, B, C, D, and another one is Hindi or Tamil. So we need a representation so that we can make a building block and we can infer something. Same way for the data sets, either it will be 2-dimensional, 100-dimension, or circular. So we need a representation. We don't know, either there should be a god which tells us that always there is a perfect representation, or if you don't have, that's why this deep learning era has come out. What we try to do, we just try to get a better representation. If our representation will be good, then the learning for our model will be better in that case. So the first important part in the machine learning and deep learning is representation. Once we representation is there, then we make certain assumptions, model, and once the model is there, then we need optimization technique, and then we need evaluation. How we say that, how we measure that learning or some error is going to be reduced or not. That's what the evaluation. So some metric for that evaluations are important. So three important part in every ML and DN component. So quickly coming up for the learning process, if any raw data is there in the machine learning part, what we do the cleaning of the data, we do the feature extraction of the data sets, and then any training, once we have a better feature, this you can say this feature extraction also as a representation one kind of. If this feature is good, then you know that our support vector machine or any classical machine learning algorithms perform well. And there are two different kind of, it may be a supervised or it may be unsupervised. In the classroom teaching, either you teach everything from the students, or nowadays students are also learning by their own pace. Just look at the book and learn. In the supervised learning, what happened, these levels are there. Means if you are reading learning, this is a cat, this is a dog. If I am saying this is a dog, so supervised learning, some images are there where you are saying this is the image of cat, this is the image of dog. So labeling is there. Labeling means this is cat, this is dog. But suppose you have a mobile phone, in your own mobile phone, if I say that use the classifier, be it dog or cat. But since labels are not there in your mobile phone data, if labels are not there, so you cannot do this supervised training like logistic regression, random forest, support vector machine, you cannot apply there. But clustering on your own mobile data, where I'm assuming that what I do, we don't do the tagging in the data sets and our mobile phone. So for that data, clustering algorithms, but even you can perform. And for that, either k-mean or other, so many unsupervised techniques are there where labels are not required. So what we are doing that. So if raw data comes out, we do the feature extraction, and then we get the job to be done. Another approach comes out, that's what I will talk about, the deep learning parts also, where people say that, okay, no need to apply this feature extraction and directly go with the deep learning. So what's the difference between the machine learning and deep learning models are basically this feature engineering part. In the machine learning part, whatever the input comes out, we have to do this feature extraction, and then we can apply our classification algorithm, either support vector machine, logistic regression, or even simple AI. But what deep learning people say, or this era, last 10 years, people say, who will do this feature extraction? We need some expert, some algorithms which tells that these features are important. So if you see the literatures, a lot of works you will get on this feature engineering. Later on, people say that can this feature engineering, because this feature extraction in one way is saying the better representation. And if feature extraction is poor, the performance of this algorithm will be poor. So what people said, okay, if this is the case, let the input directly give, and this feature engineering part also learn in the network itself. So this model will learn this, will do this feature engineering instead of doing feature engineering and passing as the input to the classification. Everything feature extraction and classification merge into one model, and that's what you can say the beginning of deep learning, where no need extra extraction techniques, but those things will be happened in the network itself. Only thing is that network size here in this case we increase. So representation learning is one of the important part, and this is the one of the sole reason you can say for the advent of this deep learning. So deep learning is one of the effective way to do this representation learning. So, and it uses tons of information to understand data and create knowledge. So what we do in the deeper learning part is basically we don't know which kind of representation will be better for a particular task. So we just place some more network, more depth in the network, and we thought with the hope and thought that even though it has been established through so many applications that the deeper passing the knowledge from one to other one and another one, we are able to capture some non-linear features and which are helping us to get the better result. So what happens in any representation learning, any algorithms, either deeper learning or any which we use, 2, 3, or 4 important concepts are there should be some smoothness. So what is the learn feature is there? If some new representation, if you are getting that, so if what is the X in the original X and Y is very close to the actual data sets, so after representation, this should also be very close. It should not be go far away in the new dimension or new representation. Multiple factors so that we can capture the hidden features for a particular one. And sparsity must be preserved. That good representations are expressive. Representation can capture a huge number of possible input configuration. For example, representation, if I am saying, for the understanding point of view, if the face, if I say, can we in the whole world, even though biometrics people are using to, we are saying that this is the unique representation for the human, but then later on, iris data comes out, people say eye is better to represent, and so many. For example, if for each face, if we represent that matrix value in such a way so that if I get the one-to-one mapping from this whole world, if any image comes out, then if the tagging is there, then I can tell that this is the image of K.P. Singh or this is the image of Thomas Joseph or anyone. But so many million people, it's not so easy to do this. Still, people are making fool and we are not able to recognize exactly looking at the face only, this is the face of the person, until unless we have a dictionary for that. So the representation is also the very important part. And if we are able to do that in this particular application, this problem of face recognition can be solved. there should be depth and abstraction in any representation, and there should be abstraction and invariance. Deep architecture can lead to abstract representation because more abstract thought process will be, more abstract representation will be, then it will capture more diverse kind of data sets. That's what the advantage. Though those who are aware only can understand, but this is the advantage why we need abstract one, so that we can apply in the, instead of one particular kind of, if I'm saying the image, the representation of cat will be different, the representation of dog will be different, representation of human face will be different, the representation of natural images will be different. But somehow, suppose if you can represent every image in this world, there are infinite images, but countable. If we have a representation, for every image in this world, though you can count, but it's infinite possibility and unique not possible. But with the hope of that better representation, so that every image we can classify, even though theoretically, what I am saying, practically not so easy to do that. If we do a one representation where every image in a unique way can be represented, then many job is done. But we are not able to do that perfect, and so why so many deep learning architectures are there for even for a particular task, and no comparison. One is performing for a particular task, another one is performing a particular task in a better way. So there are so many techniques. I will not go in the detail. So there are in the deep learning also deep belief, deep boldment, convolution. So many techniques are there. So there are so many deep learning part. I will connect this why this deep learning and weights are important through this security. I'm coming ahead for that. One more important part, those who are working with AI ML is transfer learning. One of the important phenomena in the last 5 years in the deep learning domain. What is this? Especially transfer learning comes out. If you see after 2016 onwards, so many applications. Because training is what the idea is, even the Google, Facebook, everyone, Amazon, everyone a huge resource. Big server, so many data sets, which as a user, as a researcher on the desktop, we cannot do that kind of computing. So what is the transfer learning advantage is, as a layman, you can understand something if had been learned in one domain. What I said that something if you have learned on your mobile data sets, can we use the same machine learning model in your friend mobile data sets? Mobile data sets I am saying means all the images there in your friend mobile phone. Because the type of images will available in your data sets, the different kind of faces, and in your friend data set is different. So machine learning algorithm trained in this data sets, one mobile set, this data set now uses, can we apply the same model in this data sets? If yes, then how we can, and if not, then how we have to adopt this model to work from one domain to other domain. Another application, what you can see, those who are working, this Google, ImageNet, all they have trained such a deep learning models, and people are transforming those models, such a big model, in a smaller data set on their desktop for a particular application. What they do, they just borrow their weights from their domain. Instead of training the best weight, you just pick from that trained model, and you adopt quickly some weight of those models on your own data sets. So it will save huge computing power. Only thing is that the weights from there you are sharing from other place. So transfer learning is basically the sharing of knowledge. Sharing of transfer learning means either you share the machine learning model or you share data set from one place to other friend. For example, can you give your own all data sets images to your friend? If not, because we want privacy, here the privacy comes out in the play, which I will connect later on. There is one of the issue in the application. We want the machine learning to be adaptable, but at the same time, don't know data I will not share. Now the model is sharing the data, then model also can breach the privacy. So how it will be handled, it is one of the application of differential privacy, which later on I'm going to cover. So what happening is this, I will not go too much in the inside of the mathematical derivation of this, even though it is here, but I will try to avoid those too much mathematical derivation for this. So what I said that in any traditional or this ML algorithm, what we do, a model, we took the data sets, we choose any model. If I'm saying model, model means it may be a machine learning model. So it may be a support vector machine, logistic regression, decision tree, artificial neural network, or any other algorithm. We took the data and train, and then we do the task. Another the data comes out, again we choose another model, again we do the training, and we do the task. In this, traditionally what we are doing, one algorithm in it, you can understand, every time we are doing the training. Here in the one data set, we do the training, and another data set comes up, again we do the training. We are not passing the knowledge from this to this in any way, either in the model terms or in the data, because data we don't want to share. So the transfer learning comes out that way, the knowledge sharing as a human mind, how it works. If we recall, as a human brain, if someone is good in programming in any language, I'm saying programming, so no need to teach that whatever the difficulty he or she has faced during the learning of any programming language, he or she is not going to face same kind of difficulty in the learning of a different language. If someone has the knowledge of C, quickly he can adopt and do the programming in Python. It's not then a big job. The same kind of transformation of model or knowledge, how we can do in the machine learning. And that's what the transfer learning in the machine learning is. So either transfer knowledge from previous domain to the target domain, or commonality between task and domain. What are the common things? Then also you can, there are many smaller and big issue also comes out in between. Play, because saying is much easier, but doing is difficult. Why transfer learning? What I said, that data sets unavailable or expensive to produce, procure also, or sometimes if big data is there, so we cannot do that kind of computing in our machine also, even though this one it will be helpful, especially in the medical domain, where you don't want to, because every hospital have a data sets, but if you ask to give the data sets in one place, no one will share, no individual even give the permission. So that structure using the privacy preserving part, the federal learning, which I'm going to cover more. Before that, just understand the issue, and different kind of learning algorithms are available. So these are some formal definitions of transfer learning. This part, though I used to talk about what is happening is there. What is transfer learning basically means? X and PX means data sets is there and their distribution is known to you for data sets, and this is the task. Task is to for learning this function and this level Y. Task T is defined by a level space Y. Predictive function which is learned by the feature vector and level pairs. So to sum up, we have a data sets and the task on this, and then given a source domain task. So source domain means one data set with corresponding source task TS. One task is defined for this data sets, and a target domain, another data sets. Target domain, if I am saying, means another data sets comes out where you can say that your friend mobile data set with a target task theta. The task will also be different. It may be same. This task, target task and source task. This task both may be same or different. Also, transfer learning is the process of improving the target predictive function. Means, can the learning task, if you have learned something on your data set using machine learning model, using this learn model, you want to improve the performance of your machine learning model on your friend mobile data sets. this is what the transfer learning is. But you want to use the knowledge which you have gained during this process of learning on the source domain and the target domain. This is what the transfer learning is. There are many kind of doing this transfer learning. One is instance based, means some particular data sets you can share from one domain to other. You can share some feature also. Some feature you can share from one domain to other domain. Another one is the parameter sharing. Parameter sharing means, suppose if you are aware about the regression model. So in regression model is y equal to wx plus b. So w and b are parameters. If you change the data sets, w and b will be changed. So parameter sharing means in one domain, if you have learned the parameters w and b, can the same w and b we use in a different your friend model? And that's what in the maximum now the transfer learning also people are using. If you have the knowledge about this ImageNet and all those kind of available big deep learning models, we try to take the model developed by the Google or Facebook, but we adopt using transfer learning phenomena on our own data sets. This is the one of the implication or concepts of transfer learning. Instead of doing and training again VG16 and 19, those structured from the scratch, why? Something has been learned from the bigger structure, we just adopt on our own data sets. This is the parameter sharing. Relational knowledge, some relationship between source and target. If we establish or distribution of two, we can make a similar, then this is also one kind of transfer learning. Trained on one domain can be adopted to other domain, is what I said. So even though quickly, I will just 1 minute, I will take water then. There are different kind of transfer learning algorithms are available. As you go in detail, it's not a unique way. It's just sometimes what happens if you I want to transfer from one domain to other. So source domain and target domain, there are two, and there are many variants. If you go in the literature, it's maybe inductive kind of transfer learning, transductive kind of transfer learning, or unsupervised. What it means in a source domain, we don't care means about the label. So in source domain, if you have the labeled or unlabeled data, we have a data sets, either labeled or unlabeled. I'm not caring. But in the target domain where we want to use this model for the improvement, that data set must be the labeled one. So that kind of transferring the knowledge is inductive model. Another one is if the source domain is labeled, target domain is unlabeled, then this is transductive transfer learning. Another kind, if in the source domain and target domain, in both cases, labeled data are not available, this is unsupervised. Now I will talk about on this self-taught learning, which is the example of if source domain data sets labels are not available, but target domain data sets are available. This is the self-taught learning. And multitask, if this one is available and this one, both are available, source and target both are available. So I will talk about the self-taught learning. Means, for example, I have a mobile data which is unlabeled, but if you want to use my data, my knowledge learning, machine learning algorithm which has been trained in my source data in your own data set, which is labeled one, this kind of learning is self-taught learning. So briefly, I will talk about the self-taught learning. Or the example is, we have a self-taught learning. So what is the example? In the source domain, we have the huge number of images. And these images are not saying that this is the image of building or this is the street, so many people are here, this is the horse, or this is the natural site. That tagging is not available. This is the source domain. This is the target domain where the images are, you are saying this is the car, this is the motorbike. But very few data sets are available in this case. What you want to do now, Here data sets are very less. Only maybe only one or two image of car, or any one or two image of motorcycle. But can this knowledge of this bigger data set will help us to learn if new car is coming, then classify that new image is coming, sorry, is it a car or bike? This is the self-taught learning phenomena. And in my lab, we did some kind of experiment with this. And we have shown that this also it was in 2008 or 9 by the NGNG and other have first started this. Later on, so many variants of this algorithms have been developed. So one thing is that for this is unlabeled data. So for this part, let the application use the autoencoder. Autoencoder is one kind of machine learning algorithms which are useful in the unlabeled data. And the purpose of this autoencoder is extract the features. I will show you how it quickly. A class of neural network. The whole idea is, suppose we have a deep learning models. Okay, this is the model. Give the input. Suppose my face I am giving, and I will pass through the channel of neural network or any network. And then again, I want to generate my own image. It's not like copying, just to put here copy. I want to extract the feature of my image. Let this is the feature extracted. From this feature, I want to do again generate the same image. This is what autoencoder is. If you see the structure, okay, before showing the mathematical structure, suppose this is my own image. If I am giving my own image, I will get some hidden layer here, or it means kind of embedding. Again, from this hidden layer, we want to generate the same my own images. In this whole part, we want to learn the value of this hidden layers, which are able to again regenerate the same image. This is the autoencoder. This part is encoder, this is part is decoder. Means any new image you give or any image you give, we'll do the encoding, some another representation. One data is coming, I will represent here, and from here again I can generate the same image. This process is known as autoencoder. And to what we do in this process, basically we measure that again the distance between x and x cap. We try to minimize the x and x cap, and the bargain of this, at the minimum of this, we are able to get the weight of this hidden image. As this x cap will be closer to x, this will be a perfect representation for a particular representation. So this is the encoding. If in my source data sets, huge image sets are there, and if we do the encoding, if we apply the autoencoder in that, then what happens? Each image will have a encoder part. So it means each actual image passing through the encoder, autoencoder, will be represented in a different way. Then we will cut down this part and we will remove this, and we will use encoder part as a representation for each image. That's what I said in the beginning. Representation learning is one of the important philosophy behind the deep learning part. So somehow autoencoder is applicable for self-taught learning. We do this. There is a mathematical representation. What I said that the reverse engineering I am doing right now to make understanding. We want to x minus x cap minimize. We want to norm of xu minus x generated should be minimum. And in bargain, during this process of minimization, we want to achieve the values of all the parameters of this n and R deep network. What is this xui and xu cap? Mathematically, if you go in the reverse direction, this is nothing else but first part. Now I will come to the first. Each image will be first transformed through this vector. This is the neural network. This is the hidden layer embedding. And then from each hidden layer embedding, again, you write a function. EU means encoder weight and DU means decoder unit. So first encoding, we will get a new weights for hidden vectors. Again, from this hidden vector taking as an input, we will get XU cap. So from XU, we are getting XU cap. And finally, we want to minimize. This is the autoencoder part. So inbuilt functions are there, so I'm not going to that. And then what we did, one quick. So weights are important here. What you are saying in the source domain, some encoding we did, and that now in the target domain, what happened? Even though labels were there, what we did, we passes through that data through this encoder. Whatever you have learned the encoder in the source domain, we have just passed that our target data, which are very small, 2 or 4, through this encoder. So for each target image, you will get new embedding. And then for that embedding, you apply the classification technique, either a support vector machine or NN. And then this is the one way from the source domain, we have passed the knowledge. This embedding of source domain we have used for the target domain, and it has helped us to improve the accuracy also. What we observed through the different simulation, that in the source domain, if you see, even in the source domain, if without transfer knowledge, if you use the SVM, the advantage of transfer learning is if source domain have lesser number of data, target domain have less number of data. Like if only 5 data or only 1 data in the 10 data, you see if there are 50 data, accuracy of plain SVM is increasing. But if you are using the transfer learning concept, even with the 5 in the target domain or 10 data in the target domain, using this encoding and source domain knowledge, accuracy of the model improve. And these are the features are means hidden layer, how many units you want, 32 or 64, 128 and all. So it helps. And there are different data sets we did the experiment and it was there. Even though further, you can thought about the many machine learning models. Embedding have a many different way to do that. Quickly, one more convolution autoencoder than another experiment, even though there are so many, quickly I will. What it means, what I said, the encoding either by the one layer, hidden layer, or by the convolution, so many embedding of the layer. This you can say green and blue is encoding, and this orange and yellow is decoding. So there is no unique way. If you ask from me, how many hidden layers, how many units, you cannot say that, okay, you do the experiment and see that which one is performing well. So that this, what is important part is this representation. How much this representation we are able to extract, and again we are able to reproduce the same images. The bargain of this producing the same image is the idea is learning the different better representation. As better our representation will be, the transformation of this embedding to the target domain or in any other application will be helpful in application. We did this experiment also, and we found that this is also performing autoencoder and the same transfer learning concept. We have seen that it also performs well in a different application. This is the idea of this. So there are so many challenges, nothing is perfect. So like knowledge gain when doing transfer learning and its quantification, how much should be transferred, how should not be transferred. There should not be a negative transfer learning, means benchmark available method, unification of transfer learning due to vast amount of formulation. So many models are available. So there is no way to say that always you go with this or that. Look at that different pro and cons and then choose that which model will be good. I will not go in the zero shot, but quickly there are huge applications of transfer learning here. Also, like as a human, one application is zero shot learning. What you can say is of transfer learning. I still a lot of works are going on, current state of the art in this. For the training, just see the image of this dog and cat. What the machine learning and deep learning models are basically. In the source domain for the training, this is even the image sets are less, but at least that image is available for the training. It may not be the different images of that, but some images are available to know that this is lion, chimpanzee, or tiger. But what GeoSort's saying, like the no image of cat is here during the training, and no image of target is there. And still, how we can make adaptable to our learning model to understand this images of dog and cat. That's what the geo-sort learning, and one of the very huge application of this in many different domain. You can see that. So there are so many applications of transfer learning. Something if you are doing tagging for this image, means image we are doing the tagging or looking the or are doing the words. Can we use the same knowledge for the different? We are sharing or weights we are sharing. So challenges what comes out in the practical application. Now I'm coming quickly on that. So there are so many applications of transfer learning. Another important phenomena. So transfer learning, you have seen that we are transferring knowledge from one to other. So challenges and issues are security issues are if someone will know the data sets, then they can do the. And that's why in some real life application, people are not using that. Even the weights of the model, some sensitive data sets model, if are available, someone can misuse that. So where the privacy and the security issue comes out, and still people just in the last 2-3 years, people have started working. So before going to connect on that, one more important phenomena currently is one transfer learning and then meta learning. What is happening in the meta learning is idea is just I will say to learn that how the learning is happening, what it means to learn that how the learning is happening. What earlier machine learning models happened, we have a huge data and then learn the whole things in this. We have a huge data sets and you do the learning and do the parameters and estimation in that. But at the same time, this is meta learning is also useful for the security cases also. If one data, let like this, n data sets are doing have S1, S2, n data sets are n different data sets are available. So do the machine learning here. The same model learn here, same model learn here, same model learn here. So from same model and like 2 or 3 data sets are there. And if you apply the meta learning, and what is the learning to learn is observing that how the model weights are going to update from one data set to other data sets, how the parameters are going to change. From data sets we are, so there are so many meta learning concepts nowadays people are using instead of using the complete data sets and then making them transferring. What people are thinking, can we do that small data sets, different kind of domain data set, do the learning here, do learning here, do learning here, again, and in the bargain of this process, try to learn how the weights are going to update and change. The idea is if any new data sets comes out, then accordingly weights will be updated, and so that that model will perform well. And even though this meta learning concept is very useful for to deal with the security issue in the machine learning model. I will connect this because this is also important part, because the idea of application in the security point of view, what you can think that if 10 people are in 10 different application data sets are at 10 different place. So model will be learned at this place, model will be learned at this place, and accordingly, a general model will be developed. No data sharing will happen. So meta learning, and you can say the security issue can be solved using this meta learning concept. Also, how it will be, I will come up. So meta learning is one of the important part. Okay, looking at the time, I will not go too much. I will talk about one thing I have put it there, but meta learning I will not talk. I have some. I will talk about the challenges in this. Let's come to the security issue part, because here I want to connect more on this. So what is the challenge? So many AI applications or machine learning, deep learning models are available in terms of transfer learning, meta learning, but still there are two major challenges in adopting artificial intelligence and machine learning models today. What are those? Data is in most industries exists in the form of isolated isolate. What I said in the initially, we want to make like the health data. Sitting in the Chennai, maybe cancer hospitals there, they are keeping the each individual informations or suppose for the COVID-19 people have developed this X-ray image of the chest and then using that and saying that this is a pneumonia case or not. But what is happening? Each center which are doing this X-ray, they are keeping their data in their own place. They're not sharing in general. Even though in India, these laws are not forcefully, people are applying breach of privacy, but once you go as industry, then it will come out. So many data sets are available in a different location, and even let for the example, big hospitals have that so many X-ray images. So even if you apply and if you want to make any good model based on this, even though so many huge data is available in Chennai-based hospital, but if as an industry, suppose if you want to collect all the data in one place, then no one will allow. No cooperation, no policy right now. Our policy is saying you cannot do that because security issue, individual health issue, I cannot give you all the individual detail. Otherwise, as an industry, you will bargain and you can share this one with the health insurance company, and then accordingly they will increase the price of the health insurance. So there are many misuse also. But at the same time, whatever the drawbacks are there, but at the same time, there are very much utility of that. If we have the whole data sets, larger data sets, our machine learning and deep learning models will learn in a better way, and accuracy and our pattern recognition will be better. So how we can do that? This is the one of the important isolated form, and this is the important issue and challenge. And each government have a different policy also. No one is saying that just do this and took the data easily. Even increasing demand for privacy preserving in AI. Whatever the AI and all we are using, the privacy is important. Like for example, if I'm giving, we all have, very rare, have this, those who are attending this, at least this workshop, on the mobile, at least everyone have either Flipkart or Amazon app. What you are doing or we are doing, whatever the purchasing we are doing, they are reading the pattern. They are knowing everything. As Amazon is a big company, so many user data sets they have, and they are able to predict in future what you are going to buy or what you are going to not buy. They may misuse also. If somehow after down the line 10 years data will be rich, they can say that, okay, as a KP Singh, now I'm going to buy shoes in the next day. Accordingly, he or she may increase the price, no discount, and then you will say that, okay, that discount is not going right now. I'm talking about the negative sense. So there may be a misuse also for the data sets. This is e-commerce platform, even though something had been breached, it is not harming directly to us. So as an individual, we are not worried. But at the same time, some more health equipment you are buying, then they may infer something important. They are keeping as it is with them, okay, no issue. But later on, they may play with your own data and they can share with other individual also. Okay. Health insurance company, we can see that what you are buying, because very soon medicines will also be available online. So privacy is important in that case, but at the same time, learning algorithms also we want to be more better. We need more data. So these are the two important parts. Data are in different location available, and privacy of the AI is important. Conventional AI approaches based on centralized data, what I said, that collect data in one place and apply ML and DL, cannot meet these challenges. We cannot solve these two issues with the centralized data. How to solve the problem of data fragmentation and isolation while complying with the privacy protection laws and regulations is a major challenge for AI researcher and practitioner, especially what I said for the health issue, even the land issue and all. Even though we are so, each state country have a different law, but at the same time there are huge advantage if the data is a oil. So as much as oil we have, that efficiency of the learning algorithm will be improved. But how to make data to be available or model to be available with these privacy issues? So there are two important concepts what people are working now, and as researchers, people and industry have also developed, even though that I will touch. One of the important issue to deal with such kind of issue is federal learning and what it means. I will go in detail further in the coming slides. So what is there? Federal learning means this is one local storage, one you just see at the bottom of this graph figure. This is one local storage, this is one local storage, this is another local storage. So one model, this is one way. Federal means federal structure, federal democracy, if you are aware about that. So the same kind of thought about in this learning. This is the framework of learning. It's not a machine learning, and this is the framework where the machine learning will participate. What is the idea is, we have a training global level, we want to train something, some parameters. But these people or this country or these individual don't want to share the data. So, okay, don't share the data. Then you have a data, you do this, whatever the training and inferencing past, and this model you share with me. Data lake globally is there. So training in the data lake. So data lake is there, but this is like a coordinator. You are not going to store this data to this data to this. But data lake, you can, what you can do here, you do your training of machine learning at this part, and you share some knowledge of weights of the machine learning model to this. Again, you can weights. This weights may be shared by this fellow to the second layer, and then you accordingly they will adopt their model, and again they will send to those updated weight to the central level. Again, this weight may be shared to the third level, and accordingly vice versa, fine tuning will happen. The bargain of this, what will happen? Data will not be shared, but what they are trying to share, that parameters of the model, and then in that central level they will learn the better model by utilizing this whole available data sets. And this is one of the federal kind of learning. Still, some up to certain extent data privacy issue had been solved, but there is still a challenge that I will come up. But this is one of the framework what people are using nowadays. Okay, don't share the data, but the model parameters you share, and you make global learning parameters, which may be applicable from here. You can think about the meta learning concept also, which I discussed. Can we apply meta learning here also for the federal learning concept to solve the problem? This is still new issue where people are working. It's open kind of, still a framework people are designing, because this communication is happening. During this communication, online infrastructure are required. If someone will take the weights, then what he or she can play with the weights. If the weights of the learning algorithms are available, adversary have some knowledge about the weights, some individual data, can he leak and attack on these data sets? Again, those issue comes out in the play that we have to solve. But this channel security are important issue, which the weights, which if you are sharing. But in the federal learning, through this structure, we can do that. So FL is an algorithmic framework for building ML models that can be characterized by the following features. There are two or more parties interested in jointly building a model. Okay. Each party holds some data that it can use for model training. If I am one party and you are the other party, so we all have some data, but we don't want to put all data in one place. This is what in the model training process, the data held by each party does not leave that party. Data will be with me. The model can be transferred in part from one party to another under an encryption scheme such that any party cannot reverse engineering the data of other party. This is the important part. Even though individual information we are not going to share, the model we are going to share, but we have to do the encryption in the model such that using the model, no one can do the reverse engineering and can infer about the data. And for this particular task, differential privacy in machine learning was introduced, which I will touch after this 1 or 2 slides. For the encryption purpose, also an important part how we can do that, and differential privacy is one of the way of doing machine learning in machine learning or in deep learning. So what I am saying this, encryption is important here such that any party cannot reverse engineering the data of other parties. And the last is also the performance of the federated model is a good approximation of an ideal model built with centralized data. No doubt if all data in one place, then the learning algorithms have performed better. But if data sets are not coming in one place, we cannot do that, laws are not supporting, then even in that case, how this federal learning structure will be helpful to build up a model. I'll show you 1 or 2 examples. In general, it can be categorized, and one bank, online banking is there in the China, WeBank, they have used this process to develop what there are 2 main category you can say for the federal learning. One is VFL, that is vertical federal learning. What it means, in data sets, if you have about the knowledge of data sets, in general what happened, the row wise we are say the instances and the column we say as the features. Okay, so what vertical federal learning is saying, for a KP thing, for me, for the banking purpose, I am doing a shopping, suppose. So my shopping pattern features are available with that shop. And also if I am going to the health sector, so my health sector related features are available to the hospital. As an individual, I am common, but different features are available at different source. So it means the raw data, individual instances are there, but some properties are available in one place, some properties are available in other place. Both if combined, they share, then some more better or more different kind of pattern they can infer. But the data they don't want to share. In that scenario, the vertical federal learning, vertical means some features are available in one place, some feature in other place. But the common data, but features are at Am I audible?
Yes, sir, audible now.
I lost the connection, so I am sharing again. Sorry.
Sir, okay.
So is it visible now?
Sir, are you there?
Am I audible?
Now we can hear you, sir.
Some problem is from my end or?
Sir, I hope it is from your end.
Okay. Now my screen is visible?
Yes, now visible.
Okay. Sorry for interruption from my end.
It is fine.
Okay. Okay. So I hope I was audible till this vertical federal learning. So next one, what horizontal federal learning, what I was discussing is some data, full data, whole row you can say is available in one place, another row is available in one place. And beautiful application for this is federated vision computing. And basically the idea is even in the edge, based on the edge computing, people have developed this model. Okay, it's a vision computing. So quickly some video is coming and just do this, learn the task and share the weights in one place. Or some task, some video in one location is coming, so many locations, you just share at the centralized. Instead of sending the video at every place, update the weight and send the weight to the central level. This is what the horizontal federal learning structure. You can see here, the more I will talk about this federal vertical federal learning, there are two scenarios. If you see in the right side picture, there may be a collaborator which are seeing that, okay, data from A, okay, first one sending public key and then exchanging intermediate results to them. 1 and 2 just share, and then again you just exchange everything to the B. Here only the results you are sharing, nothing else. You cannot share, no data exchange. You just see in the left side, A and B cannot share the data. What they are doing in the left structure, you see, you do the encryption, whatever you want to do, learn your model here. B will learn separately the model. They will share the model weight to the central level, and then their weights may be shared. B will share the model's weight to the here. They will update here. The federal learning will update the weights. He may share the recomputing of the weights based on these two weights and send to the A and B again. And then he can say that, okay, do this again, recomputing on the base of the modified weight, and through this learn the weights. No one is sharing no, A and B are not sharing the data at all, but they are sharing the weight to the central level. This is what the federal machine learning. But here also the weight privacy is also important, comes out, not only data. So how this weight also be in such a way so that even if the person will know this weight and one or two actual data sets, even though he cannot infer about the other data. That's what the one of the issue is. Because as an adversary, if someone is knowing the weights and some data, then he or she will try to know the information about the all data. how to do that? Again, making the privacy, differential privacy in this learning model is also one of the important concepts where security features have been applied in the machine learning model with development of the learning model. I'm not talking about the data privacy and data should be preserved only. How the weights of the learning model also can be made this privacy can be introduced there. Just I will introduce in this. Another vertical federal learning is there is no collaborator which tells I do this and that. Only that you just update the weights here. This is, if you see the first one, there is a collaborator here, but in the second case, another kind of example, there is no collaborator which is collaborating and doing some analysis. Just you share the weight and you will get here. Means you just extend the weights only to A can share the weight to B, B can share to A, and then bargain of that, they can update the weights overall of the structure. So this is one kind of federal learning structure. But the issue, what I said, is how to make secure transformation of the weights. And for that, another important concept last 4 or 5 years, you may see and Google it and see that huge work on that, and also my lab is working in this, making differential privacy in machine learning. The whole idea is for a data set, not data sets is okay. The weight also should be learned and make secure in such that if someone will know the exact weights of the learning model and some actual data set, he or she cannot do that reverse engineering and can infer about the data set information. And this is one small application I will share with you. So why we need that? We don't, machine learning models may leak sensitive information during and after training of the model. May leak means someone can take the weights in one case and then they may do the reverse engineering. So to handle this, differential privacy makes machine learning models combat such attacks. So for that, differential privacy had been introduced to make. What is differential privacy? See, if you know about the differential privacy for the data sets, the same concept is here. It guarantees that the attacker can learn virtually nothing more about an individual than they would learn if that person's record were absent from the data set. Means if one or two information if you have, you cannot know about the data sets. That's what the differential privacy have the important you can say feature. And this one you can apply with the machine learning models. Where you can apply in the machine learning model, I'm focusing on the machine learning model by adding randomized noise to different stages in the machine learning model to protect individual entries without significantly changing the results. Means some weights we want to learn with noise such that, okay, if noise there, one or two data will come, you cannot do the reverse engineering and get. But at the same time, with the bargain of adding the noise, we don't want to lose the accuracy too much. So there are many ways you can do that, either activation function or output. One example I will give you can be achieved by adding randomized noise to an aggregated query results to protect individual entries without significantly changing. For example, you can understand. Suppose this one is, I'm assuming that you are knowing about the artificial neural network. What we do in the artificial neural network or any least square, any least square method, in general, we have a function, mean squared error function is 1 by n summation y minus y predicted square. And this is the last structure and number of, and so softmax is used for activation max function. This is everywhere softmax used for the neural network. What the idea is, you use the differential privacy in that case. In the error function I want to introduce, so other part I'm just skipping that, how you can do that in your model, any different model. Intuition is to share learned parameters, what I said that. Parameters of the model we want to share. So what we added, Laplacian noise in the error function. That's all. And what is Laplacian noise? recently we have proposed this DPN and differential private AN, and it was published in one conference. So, but the idea was what I am telling you, to add the noise, Laplacian noise in the many different locations. One I am sharing to you is to Laplacian noise. You add as a noise. What is the formula for Laplacian noise? It's common, like Gaussian noise. Though Gaussian noise we are not using, Laplacian noise. What will happen? The structure will be like this. Your error function will be plus Laplacian noise. So some noise in the error function we have added. And in the bargain of this, what will happen? Now we try to minimize this. And we observed that almost same accuracy were coming, almost same. But at the same time, the weights will be different. Instead of the exact weight with the noise, some weight values will be modified. Not all will be modified, but some will be, because the noise has been added in the error function. This is the Laplacian noise, and this Laplacian noise in differential privacy have the property that violation of one data sets or something cannot leak the other information. So we borrowed that concept and applied this here. So what advantage is that through this privacy noise in the error function, even though in different places also you can add, we were able to achieve this differential privacy in the machine learning model. And then, even though this may be helpful, I'm saying may be helpful, so anyone is working may do the experiment also, because all these are current research where security in the machine learning with the help in the federal learning, all machine learning models are needed. So what I said, we achieved up to a certain extent, still the work's going on in this direction, is to introducing differential privacy in the machine learning different models. We are doing the experiment. This is the raw one and the simplest one I'm sharing right now with you, where you can think about to apply the differential privacy. The utility will be if we are able to make a differential private machine learning models and accuracy, we are able to achieve the same what the plain model is giving. Then in this federal learning structure, this kind of machine learning model will be helpful to preserve the data security. So with this, I would like to stop here, and I'll be happy to if audience have some questions regarding this. Thank you. And I will take some questions on this. Better, I will take some questions. If you have, please ask some questions on this so that I can say and discuss.
Thank you, sir. Participants, if you have any questions, please unmute and speak, or you can use the chat window.
If anyone have any question related to machine learning or this differential privacy in machine learning or federated learning, which is very good area where you can work the security in AI basically, which is very, very helpful, where you can think about to work, even those who are willing to work in the current combination of AI and machine learning with security. Anyone have question? Then no one?
Sir, in healthcare, especially in the background of COVID-19, though data is and can be available, as you said, but there are critical privacy challenges.
Yes.
How do you think that meta-learning can be helpful in overcoming the privacy challenges in such?
That's what I said. Meta-learning with this federal learning structure. The idea is in the meta-learning, the machine learning, we try to learn the parameters of the weights. But at the same time, what we are in the meta learning from one domain to other domain, we share the weights. Okay.
Okay.
But what I said, that we can use the differential privacy or any encryption on those weights so that no one can play with those weights and do the reverse engineering in getting again the actual data. So this is the upcoming. You will get not too much work, but works are coming. This is the current research where people are working to combining this security in the machine learning different phases, so that in the more, especially in the healthcare, where people don't want to share the data, and security prime concern. So in that case, if you make machine learning model more private and secure, then the parameters can be shared with any individual to play with this and get a better learning model.
Okay, thank you.
So in the practical application, this is very, very helpful, even though some industry has started way back. So very soon, within few years, it will be in the norm. Too many will use this.
Okay, okay, sir.
Any
other participants? Okay, thank you, sir, for the spectacular session. I believe that the participants got many inputs from your session and you have motivated them to further read and study on the topic. On behalf of the KCG College of Technology, I thank you for taking time out of your busy schedule and giving a wonderful talk. Thank you, sir.
Thank you. Thank you for inviting me. And if anyone have any questions on this, you may share my email ID, and if they want, they can discuss, and I'll be happy to. Anything if they need help to understand any concept, I'll be happy to share that and discuss.
Okay, sir. I think it will be helpful if you can give your email ID and phone number here.
Yes, email ID already I shared, that kpsing@iit.ac.in.
Okay.
The same ID, yes.
Okay. Okay, sir.
Okay. Thank you. Thank you for listening.
Participants, the feedback link will be shared shortly. Please fill it.